December 1984. In Antarctica's endless white, a scientist picks up a 4-pound rock. Ordinary, until a decade later when NASA declares it may hold traces of Martian life. The world freezes as a single space rock, Allan Hills 84001, sparks the most explosive debate in astrobiology and triggers a presidential address. For years, its origins and the secrets locked inside have split science. But here's what the headlines never told you: that Mars meteorite is just one of nearly 300,000 cosmic visitors hiding beneath Antarctic ice, unknown, priceless, and at risk of vanishing forever. So where are they? And could another stone rewrite everything we know about Mars? On the windswept ice fields of Allan Hills, Roberta Score bent to examine what looked like just another dark stone half buried in the Antarctic blue. The date was December 27, 1984. Her team, part of the Antarctic Search for Meteorites project, had spent weeks scanning the endless white for fragments fallen from space. This one weighed just under 2 kilograms, heavy in the hand, but unremarkable among the thousands cataloged each season. Logged, bagged, and shipped north, the rock joined hundreds of others in the curation vaults at NASA's Johnson Space Center, its story seemingly finished before it began. Years passed, thin slices were cut, minuscule samples set aside, and the meteorite, labeled ALH 84001, waited in storage. Then, in 1994, a routine analysis changed everything. Scientists drilled into tiny pockets of ancient gas sealed inside the stone. The chemistry was unmistakable. The ratios of argon, nitrogen, and xenon matched the thin, carbon dioxide-rich air measured by the Viking landers on Mars in 1976. For the first time, a rock collected on Earth was proven, beyond doubt, to have come from the Red Planet. ALH 84001's journey had begun billions of years earlier. Radiometric dating revealed its age. Over 4 billion years, older than any surface on Mars now exposed to space. Around 17 million years ago, a colossal impact blasted it free from Mars's crust. It drifted through the solar system until, about 13,000 years ago, it landed in Antarctica, preserved in ice until Score's team found it. Chain of custody records, sample logs, and curation notes from NASA and the Antarctic Meteorite Laboratory document each step from field to laboratory. Thin sections and gas samples were distributed for analysis across the world. The stone's Martian fingerprint, its trapped atmosphere, became the gold standard for identifying Mars meteorites, a method still used today. What began as a routine field collection had, through careful provenance and a single test, turned into one of the most significant extraterrestrial finds in history. The ordinary became extraordinary the moment its true origin was revealed. A Martian relic, older than any rock yet brought back by spacecraft, waiting in the ice for its story to be told. August 7, 1996. Cameras clustered in the morning heat outside the White House Rose Garden. President Clinton stood at the podium, flanked by the American flag, and told the world NASA scientists believed they had found evidence of ancient life on Mars, locked inside a meteorite from Antarctica. The words carried further than any laboratory paper. Headlines circled the globe within hours. Television anchors called it the most important scientific announcement in a generation. For a brief moment, the question, "Are we alone?" seemed to demand an answer. Inside NASA, the team led by David McKay, Everett Gibson, and Kathy Thomas Keperta became overnight celebrities and lightning rods. Their science paper outlined 4 lines of evidence: organic molecules called polycyclic aromatic hydrocarbons, carbonate minerals shaped in patterns familiar from Earth's bacteria, perfectly formed magnetite crystals, and tubular features that, under a microscope, looked like fossilized microbes. Each detail was scrutinized in newsrooms and classrooms from Houston to Tokyo. But the celebration was short-lived. Within days, skeptical voices challenged every claim. Geochemists pointed out that polycyclic aromatic hydrocarbons form in space and can seep into rocks over millennia. The carbonate globules, they argued, might have grown in hydrothermal vents, not Martian lakes. Magnetite crystals could arise in the heat of an impact, not just in living cells. The so-called microfossils were smaller than any known life, and critics warned they might be nothing more than mineral growths or the legacy of long Antarctic burial. Some even questioned whether the organics might be modern contaminants carried by wind or human hands. The field fractured. At the 1997 Lunar and Planetary Science Conference, a poll found researchers split nearly down the middle. Half thought the evidence pointed toward biology, half called it inconclusive, or favored an inorganic explanation. The debate spilled into editorials and late-night talk shows. NASA's phone lines rang with questions from Congress. Funding for astrobiology soared, as did the pressure to find more meteorites, especially those untouched by Earth's biosphere. Time did not settle the argument. Over the next 2 decades, new techniques would probe ALH8 4001's secrets. In 2020, researchers found nitrogen-bearing organic compounds inside the meteorite's carbonates, molecules essential for life, but not proof of it. Each discovery reopened old questions about contamination, about the limits of chemistry, about the fine line between life and geology. The scientific community remains divided. For every study suggesting a biological fingerprint, another finds an abiotic path. The meteorite story is unfinished, its evidence still debated in journals and conference halls. One fact stands clear: a single stone is not enough. The world's attention had turned to Antarctica, not just as the resting place of ALH8 4001, but as the greatest reservoir of unstudied meteorites on Earth. Somewhere in the ice, more Martian rocks wait, each with the potential to confirm or overturn the story that began in the Rose Garden. Antarctica's blue ice fields are not just a frozen wilderness, they are nature's sorting ground for space rocks. Each winter, meteorites rain down across the continent, scattered by the thousands over a surface the size of the United States. But their journey doesn't end where they fall. Over centuries, these stones are carried by the slow, relentless movement of glacial ice, flowing outward from the heart of the continent toward the mountains that fringe the polar plateau. As the glacier creeps forward, it acts as a conveyor belt, sweeping up meteorites from deep within the ice and ferrying them toward its edge. Where the flow meets the rocky barrier of a mountain or a nunatak, the ice is forced upwards. Here, powerful winds scour away the youngest snow, revealing ancient blue ice, hard, glassy, and streaked with the scars of centuries. It is on these wind-lashed surfaces that meteorites become concentrated, left behind as the ice around them sublimates into vapor, molecule by molecule. Under the ceaseless Antarctic sun, dark stones forged in the vacuum of space stand out in sharp contrast against the dazzling blue and white. Their colors, black, brown, metallic gray, are a beacon for field teams searching from the seat of a snowmobile. The process is not random. The ice and wind together act as a natural filter. Meteorites that landed hundreds of kilometers apart are swept into the same blue ice corridors, creating dense strike zones where dozens can be found within a single square kilometer. These conditions preserve meteorites in a way unmatched anywhere else on Earth. The cold halts chemical reactions that would weather or rust their surfaces. Many are as pristine as the day they fell, their fusion crusts still sharp, their interiors untouched by water or air. Some even retain delicate features: bubbles of trapped gas, fine-grained minerals, or tiny pockets of ancient Martian atmosphere, protected for millennia by the deep freeze. Since 1969, more than 45,000 meteorites have been recovered from Antarctica, 2/3 of all known to science. Each one is cataloged, logged, and tracked with meticulous care. The blue ice fields are not only a collector's paradise, they are the world's best preserved archive of material from the solar system's earliest days. But finding even a single stone can mean days of searching across a landscape where the horizon never changes and the wind never stops. For every rare Martian sample, there are 1,000 ordinary chondrites, each one a piece of the cosmic puzzle, waiting to be found. Meteorite hunting on Antarctic ice is a test of patience, skill, and sometimes luck. Veteran field teams wake before dawn, insulated against a wind that can freeze exposed skin in minutes. They ride snowmobiles across blue ice corridors, eyes scanning the horizon for anything that breaks the monotony of white and blue. The most experienced hunters know the signs: a glint of metal, an unnatural angle, the sharp edge of a stone that doesn't belong. Yet not every meteorite waits on the surface. For decades, scientists puzzled over a simple mystery. Iron meteorites, which should account for half of all space rocks, made up only a fraction of Antarctic finds. In 2016, a small experiment provided the answer. Researchers took a block of clear ice, embedded a chunk of iron, and shone a lamp to mimic the Antarctic sun. Over hours, the metal absorbed heat, melting the ice below and sinking steadily, until it rested nearly half a meter down. This explained why so many iron meteorites escape detection. They slip beneath the surface, hidden from sight, just beyond the reach of a boot or shovel. To overcome this, teams adapted technology once used for landmine detection. Metal detectors, tuned to pick up the faintest signal, sweep the blue ice fields in slow, deliberate arcs. The hunt is painstaking. Each beep could mean a buried meteorite, or just a patch of mineral-rich rock. Still, the results are undeniable. In the 2023 season, a detector team uncovered a specimen weighing over 17 pounds, one of the heaviest Antarctic meteorites found in a century. It took hours to extract, chipping carefully through ice to avoid damaging the fusion crust. The moment it broke free, every hand on the team wanted to lift its weight, to feel the cold legacy of a journey from the asteroid belt, or perhaps from Mars itself. Martian meteorites are the rarest prize of all. With fewer than 300 confirmed worldwide, each new discovery is a scientific windfall. On the open market, a single gram can command more than $100,000, a value driven not by collectors, but by the hunger of researchers to answer questions about Mars's past. Yet even with the best tools and sharpest eyes, most stones remain elusive. Hours of searching yield handfuls of finds, and every field season is a race against time, weather, and the slow but relentless burial that claims more meteorites each year. Manual search has its limits. The blue ice stretches for hundreds of kilometers, and the number of meteorites hidden just below the surface dwarfs those ever found. To unlock the true potential of Antarctica's cosmic archive, scientists need a way to see beneath the ice, to predict where the next great discovery waits. The old methods have revealed wonders, but the next leap will require a new kind of vision. Veronica Tolinar's team at TU Delft approached Antarctica's meteorite puzzle with a different kind of toolkit. One built from satellite sensors, algorithms, and tens of thousands of field reports. Their goal? To predict not just where meteorites have been found, but where they are still hidden beneath the ice. The process began by assembling a digital map of the continent. Each grid cell 10 kilometers across, each one marked by its own unique set of environmental fingerprints. 8 separate data streams fed into the model. Surface temperature came first, drawn from MODIS, infrared satellites. This single variable, recording the subtle warmth and cold of Antarctic blue ice, proved more predictive than any other. Hotspots, even by a degree or two, tended to expose more meteorites. Next came ice flow velocity, measured by radar altimetry and satellite tracking. These values captured the slow, powerful movement of glaciers. the conveyor belts that sweep meteorites from their landing sites toward the mountain barriers where they collect. Blue ice area was mapped using Landsat imagery, distinguishing the hard, ancient ice from the softer, snow-covered fields, where meteorites rarely concentrate. Surface slope, calculated from digital elevation models, revealed how steepness and terrain channeled the flow of both ice and stone. Radar backscatter from Sentinel-1 and ICE-SAT-2 added another layer, measuring roughness and the microstructure of the ice surface. The model also tracked the distance to the nearest nunatak or mountain, since meteorites accumulate where ice flow is blocked. Finally, latitude, longitude, and incoming solar radiation were logged for each cell, capturing the effect of sunlight on melting and burial. To train the algorithm, the team fed in over 45,000 confirmed meteorite finds, stretching back to the first systematic searches in the 1970s. Each known location anchored the model, teaching it to recognize the combination of conditions most likely to yield a discovery. But the challenge ran deeper. Most blue ice fields have never been searched. These areas were labeled not as negative, but as unknown, potentially rich ground, or empty, with no way to be certain without a field expedition. The team used a machine learning approach known as positive and unlabeled learning. Rather than assuming that unsampled areas held no meteorites, the model treated them as mysteries, calculating probabilities based on their resemblance to known hotspots. Cross-validation was performed by spatial region, not just random split, to avoid overfitting by proximity. In each test, the model was trained on 80% of the data, then challenged to predict the remaining 20%, never seeing the answers in advance. Results were measured by recall and precision. Of all the places where meteorites had actually been found, how many did the model correctly identify as high probability? The answer, averaged across all runs, was 83%. This figure reflected not just the model's ability to find known fields, but its skill in distinguishing productive zones from barren ice. The feature rankings left little doubt. Surface temperature dominated, followed by ice velocity and blue ice area, with slope and radar adding nuance. The final product was a probability map of the continent. Grid cells were ranked, the top 600 unexplored zones flagged as the most promising. From these, the team extrapolated a new estimate. More than 300,000 meteorites likely remain, hidden beneath the Antarctic ice. The model's code and data were made public, inviting scrutiny and collaboration from researchers worldwide. For the first time, the search for space rocks had a guide, one built not from luck or instinct, but from the silent signals of the ice itself. The probability map created by Tolinar's team did more than outline a theory. It pointed to action. Each grid cell, 10 kilometers wide, was colored by chance. Deep blue for barren, bright red for promise. From this continent-wide mosaic, 600 unexplored zones stood out as the most likely to yield new finds. These were not random patches, but carefully ranked sites, each sharing the environmental fingerprints of areas already rich in meteorites. The numbers behind the map were staggering. If the densities found in known hotspots held true, Antarctica's blue ice could be hiding over 300,000 meteorites, 6 times the current world collection. The 45,000 stones recovered since 1969 now looked like the tip of an immense, frozen iceberg. For every meteorite already bagged and logged, dozens more might still lie just out of sight, shielded by centimeters of glassy ice, or buried in the shadows of nunataks. This was not just an intellectual exercise. In January 2023, a field team set out for one of the predicted zones in East Antarctica, guided by the AI model's coordinates. The site, untouched by previous expeditions, lay more than 200 kilometers from the nearest research station. Within days, the team recovered several meteorites, including a specimen weighing over 7.6 kilograms, among the heaviest found in recent years. Each recovery was logged, photographed, and sampled, the data sent back to TU Delft for comparison. The success rate far surpassed previous seasons, confirming that the algorithm's predictions could be trusted on the ground. The impact rippled beyond the field. For the first time, an interactive public map allowed anyone, from planetary scientists to amateur enthusiasts, to explore the continent's hidden meteorite troves. The website, where to catch a falling star.science, displayed the AI's top 600 targets, each clickable for satellite imagery and probability scores. The data was open, the code transparent, and the invitation clear. The next breakthrough could come from anyone with the drive to reach the ice. Behind the excitement, the stakes were growing. Every season, warming temperatures threatened to bury more meteorites beyond reach, especially the dark, iron-rich stones most likely to come from Mars. The AI map offered a new way to prioritize the search, triaging sites before climate erased their treasures. For Tolinar's team, the numbers on the screen translated into a race against time, a call to action for the world's scientific community. The greatest archive of solar system history may still lie beneath Antarctic ice, but the window to find it is closing. Antarctica's blue ice fields, once thought immune to time, are changing faster than scientists ever anticipated. Weather station records near Allan Hills and the Miller Range show surface temperatures rising by about 0.15 to 0.2 degrees Celsius each decade since the 1980s. It's a small number, barely enough to feel in a single year, but over decades, the effect is profound. Even that subtle warming is enough to tip the balance during the brief Antarctic summer, when the sun stays low on the horizon and the ice absorbs just a fraction more heat. Iron meteorites, already rare among Antarctic finds, are the first to feel the consequences. Their dark, metallic surfaces soak up sunlight, warming faster than the surrounding ice. As temperatures climb, each summer brings more days above freezing. The heat pools beneath these stones, melting the ice below and allowing them to sink, sometimes by half a meter or more in a single season. Once buried, most become invisible to the eye and unreachable by hand, lost beneath layers of blue ice that can take centuries to resurface. Climate models, calibrated with decades of field data, now warn that the pace of loss is accelerating. If current trends continue, as much as 70 to 80% of meteorites visible on the surface today, especially the heavy, iron-rich types most likely to come from Mars, could be buried beyond manual recovery by 2050. The risk is not uniform. Some blue ice areas are warming twice as fast as others, and the most productive meteorite stranding zones face the highest rates of loss. Each year, the window narrows. Stones that survived for thousands of years in the deep freeze are now slipping from reach in a single generation. For researchers, the numbers are sobering. Every buried meteorite is a lost chapter in the solar system's history, a data point erased before it can be read. The urgency is not only scientific, but practical. Expeditions must now move faster, prioritize the most vulnerable sites, and adapt to conditions that change year by year. The race to recover meteorites is no longer just a matter of curiosity. It is a race against a ticking clock set by the planet's own warming pulse. Every Antarctic meteorite hunt is bounded by the harshest limitations on Earth. The field season is short, November through February, when the sun barely sets and temperatures hover just above the threshold for safe work. Outside these months, the continent locks down under darkness and cold, so severe that even aircraft cannot fly. Each expedition must be planned with precision, balancing the narrow weather window against the risk of storms that can strand teams for weeks. The price of access is steep. A single field campaign can cost between $1 and $3 million, depending on the remoteness of the target site and the need for specialized equipment. Helicopters are often the only way to reach the most promising blue ice zones, lifting scientists, fuel, and supplies across hundreds of kilometers of unbroken ice. Every extra flight, every additional crate of gear adds to the budget and the logistical complexity. Teams must carry everything they need: tents, food, fuel, medical supplies, because resupply is impossible once operations begin. International treaties add another layer of constraint. The Antarctic Treaty System, signed by 56 nations, tightly regulates all scientific activity. Every plan must be approved in advance, with strict protocols for environmental protection and sample documentation. No waste can be left behind. Even the smallest field camp must account for its footprint, and meteorites themselves are considered a shared scientific resource. No private ownership, no commercial export, every specimen logged for global study. Within these boundaries, the margin for error is slim. Teams are limited by how much weight they can fly in, how many days they can work before storms close in, and how far they can travel before fuel runs low. Each hour on the ice is precious. The success of a season is measured not just by stones recovered, but by the efficiency of the operation. In this environment, traditional search methods yield diminishing returns. Random sweeps across the ice surface find only a fraction of what lies beneath. Artificial intelligence now offers a way to tip the balance. Guided by satellite predictions, expeditions can focus their efforts on the most promising zones. In recent seasons, AI-driven targeting has boosted recovery rates to nearly 80%, more than double the success of random search. But even with these advances, the number of expeditions that can be mounted each year is limited by cost, weather, and regulation. The race for meteorites is not just against the climate, but against the practical limits of what human teams can achieve on the world's most inaccessible continent. A single Martian meteorite can raise questions that echo for decades, but the real power of these stones lies in their numbers. No matter how carefully ALH 84001 is studied, it represents only one fragment of Mars, one place, one moment in deep time. To move beyond controversy, scientists need a population, not a lone witness. Each new meteorite offers a new line in the planetary ledger. A different age, a new mineral recipe, a record of water or heat or impact. Some come from volcanic plains, others from ancient highlands, each capturing the surface of Mars as it was when the rock was launched into space. Astrobiologists rely on this diversity to separate signal from noise. If organic molecules, magnetite crystals, or carbonate globules are found in only one stone, doubt lingers. Could they be rare or just a fluke? But if similar features appear in dozens of Martian meteorites, collected from distant blue ice fields and dated to different eras, a pattern begins to emerge. Researchers can test whether potential biosignatures are widespread or unique, whether they appear only in rocks from certain times or places, or whether they vanish in younger, drier samples. This is the heart of statistical science, not just finding a possible sign of life, but measuring its frequency, its context, and its limits. The timeline for direct answers from Mars remains distant. NASA's Mars Sample Return mission, aiming to bring curated Martian rocks to Earth, is not scheduled to arrive before 2033. Until then, Antarctic meteorites fill the gap. Each one is a time capsule, preserving the chemistry and history of Mars across billions of years. With hundreds of thousands still hidden in the ice, the search is not just for more rocks, but for the patterns that will finally reveal whether life ever took hold on another world. Expeditions across Antarctica now move with a precision that would have seemed impossible just a decade ago. In the coming austral summers, teams from the United States, Japan, and Europe will converge on the Prince Charles Mountains, a region flagged by satellite as one of the richest unexplored meteorite zones on Earth. Their efforts are coordinated through international programs like ANSMET and JARE, each drawing on decades of field experience. But their toolkits have changed. Drones now sweep the ice fields, flying low and slow, their cameras tuned to spot subtle color shifts invisible to the human eye. These autonomous scouts can cover 10 times the area of a traditional snowmobile team in a single day, mapping potential targets and relaying coordinates in real time. Ground-penetrating radar, once the domain of geophysicists, is being adapted to scan beneath the surface, capable of detecting stones buried up to 2 meters deep, including those elusive iron meteorites that have slipped below the reach of boots and shovels. Satellite change detection, using high-resolution imagery from the latest Earth-observing constellations, adds another layer. By comparing images taken days or weeks apart, scientists can spot the sudden appearance of dark spots on the ice, potentially fresh meteorite falls, still untouched by wind or sun. These alerts are fed directly to field teams, who can pivot their search plans in response, sometimes reaching a new find within hours of its detection from orbit. The next wave of technology is already in testing. Robotic collection vehicles, equipped with AI navigation and sampling arms, are being trialed in controlled zones. The goal? To operate around the clock, regardless of weather or visibility, gathering meteorites that might otherwise be lost in the next thaw. International collaboration ensures that every specimen is logged and shared, with data uploaded to global databases for instant analysis. As the 2025 to 2026 campaigns approach, the sense of urgency is unmistakable. The tools are ready, the maps are drawn, and the countdown has begun. Somewhere in the blue ice, the next Martian relic is waiting. One more piece in the puzzle of life beyond Earth. Since 1920, scientists have recovered over 45,000 meteorites from Antarctica, 2/3 of all known finds on Earth. Yet the AI model developed in 2022 predicts more than 300,000 still lie hidden beneath the ice, including many more from Mars. The Allan Hills 84,001 meteorite, discovered in 1984, remains the most debated space rock in history, with its possible evidence for Martian life still unresolved after nearly 3 decades. Today, climate change is accelerating the loss of these irreplaceable samples, with recent studies warning that up to 76% could be gone by 2050. Mars sample return missions are scheduled for 2033. But for now, Antarctic meteorites are our best window into the red planet's past. The question of life on Mars endures, and every new meteorite found brings us closer to an answer. The search continues, shaped by technology and threatened by time.